Why is there something rather than nothing? This question has haunted humanity since we first gazed up at the stars and wondered about our place in the cosmos. Where did it all come from? Space, time, energy, matter, even the very laws of physics that govern reality itself. Did our universe truly emerge from absolute nothingness? Or is asking about nothing the wrong question entirely? Tonight, we embark on a journey to the very edge of human knowledge, where science meets philosophy, and where the most brilliant minds of our time grapple with existence itself. This is not just a story about astronomy or cosmology. This is about the deepest mystery of all, the question that underlies every other question we could ever ask. Why does anything exist at all? The universe around us is vast beyond imagination. Billions of galaxies stretch across space, each containing billions of stars. Planets orbit those distant suns, and on at least one of those worlds, life emerged and eventually evolved into beings capable of asking these very questions. But how did this incredible cosmic symphony begin? Scientists have developed remarkable theories that can trace the history of our universe back to its earliest moments. We can peer through telescopes and see the afterglow of creation itself, the cosmic microwave background radiation that still bathes the entire universe in the faint echo of its birth. We can calculate how the first atoms formed, how the first stars ignited, and how galaxies gradually assembled over billions of years. Yet for all our scientific progress, the ultimate question remains tantalizingly out of reach. We have theories about how the universe evolved. But what about its actual beginning? What sparked the first moment of time? What caused space itself to exist? And perhaps most puzzling of all, how could something emerge from what appears to be nothing? Some of the greatest physicists of our time have proposed extraordinary ideas. They speak of quantum fluctuations in empty space, of universes tunneling into existence from pure void, of infinite multiverses where every possibility plays out across countless realities. These concepts stretch our imagination and challenge our most basic assumptions about reality. But here is what makes this journey so fascinating. The more we learn about nothing, the more we discover that nothing is far more complex than we ever imagined. Empty space is not truly empty. It seethes with energy and possibility. The vacuum itself may be unstable, pregnant with the potential for entire universes to spontaneously appear. As we explore these ideas together, we will discover that the boundary between something and nothing is not as clear as we might think. We will journey through the latest discoveries in quantum mechanics, cosmology, and theoretical physics. We will meet the scientists who are pushing the boundaries of human knowledge, seeking answers to questions that previous generations could barely imagine asking. This is a story about the ultimate beginning, about how everything we see around us, including ourselves, might have emerged from the deepest mystery of all. To understand where we came from, we must go back as far as physics allows us, to the very moment when time itself began, and perhaps even beyond. To understand how something might come from nothing, we must first examine what science has already discovered about the origins of our universe. The story begins with one of the most successful theories in all of physics, a framework that has revolutionized our understanding of cosmic history and earned its creators Nobel Prizes. This is the story of the Big Bang, and it is far stranger than most people realize. But before we dive into the details, let us be clear about what the Big Bang Theory actually describes. Contrary to popular imagination, it was not an explosion that occurred somewhere in empty space, hurling matter outward like a cosmic bomb. Instead, it describes something far more profound and strange. The Big Bang was the expansion of space itself, carrying matter and energy along for the ride as the fabric of reality stretched and grew. This distinction is crucial because it helps us understand one of the most mind-bending aspects of our cosmic origins. When we say the universe is expanding, we do not mean that galaxies are flying apart through pre-existing empty space. We mean that space itself is growing, creating more distance between distant objects as time passes. Imagine the surface of a balloon being inflated. Dots drawn on the balloon move away from each other, not because they are traveling across the surface, but because the surface itself is expanding. Picture this if you can. 13.8 billion years ago, everything we can observe in the universe today, from the smallest atoms to the largest galaxy clusters, was compressed into a region smaller than a single proton. The temperature was unimaginably hot, trillions upon trillions of degrees. The density was so extreme that normal matter as we know it could not exist. Even the fundamental forces that govern physics today were unified into a single, incomprehensible force. At this moment, the very concepts of size, temperature, and density push the limits of human language. We are describing a state of reality so far removed from our everyday experience that our words begin to lose their meaning. Yet this is what the mathematics tells us, based on our best understanding of how the universe works today. If we run the cosmic movie in reverse, winding back the expansion and the cooling, this is where the equations lead us. From this incredibly hot and dense state, space itself began to expand, not into something, but expanding as the very definition of what space means. As it expanded, it cooled. As it cooled, the unified forces began to separate. First, gravity split off, then the strong nuclear force, then the electromagnetic and weak nuclear forces went their separate ways. The universe was writing the laws of physics as it evolved. This separation of forces happened incredibly quickly. Within the first tiny fraction of a second, the universe underwent a series of phase transitions that would determine the fundamental characteristics of reality itself. Think of water changing from ice to liquid to steam, but instead of changing the properties of water, these transitions changed the very nature of space, time, matter, and energy. Within the first second after this expansion began, the temperature had dropped enough for the first protons and neutrons to form. These are the building blocks of atomic nuclei, but the universe was still far too hot for complete atoms to exist. The temperature at this point was still about 10 billion degrees, hot enough to prevent electrons from binding to nuclei. During these first few minutes of cosmic history, something remarkable happened. The universe had cooled just enough for nuclear fusion to begin. Protons and neutrons started combining to form the very first atomic nuclei. This process, called Big Bang nucleosynthesis, produced mostly hydrogen and helium, with tiny amounts of lithium and beryllium. The proportions of these light elements that we observe in the universe today match exactly what Big Bang theory predicts, providing another crucial piece of evidence for this picture of cosmic origins. But even after nuclei formed, the universe remained opaque. For the next 380,000 years, the cosmos was filled with a hot plasma of charged particles that scattered light in every direction. Any photon that tried to travel through this dense soup of electrons and nuclei would quickly collide with a charged particle and be scattered in a random direction. The universe was essentially foggy, preventing light from traveling far. Then came one of the most important moments in cosmic history, an event that astronomers call recombination. The universe cooled enough for electrons to combine with protons and form the first neutral hydrogen atoms. The temperature had dropped to about 3,000 degrees, cool enough for atoms to remain stable. Suddenly, space became transparent. Light could travel freely for the first time. This light, stretched and cooled by billions of years of cosmic expansion, still fills the universe today. We call it the cosmic microwave background radiation, and it provides us with a baby picture of the universe when it was less than 400,000 years old. Imagine the universe suddenly clearing, like fog, lifting from a landscape. For the first time in cosmic history, light could stream freely through space. This moment, when the universe became transparent, released a flood of photons that had been trapped since the earliest moments after the Big Bang. These photons have been traveling through space ever since, their wavelengths stretched by the expansion of the universe from visible light into the microwave portion of the electromagnetic spectrum. This cosmic afterglow is one of the most important pieces of evidence supporting the Big Bang theory. When scientists first detected it in 1965, they found exactly what the theory had predicted: a faint radiation coming from every direction in space, with a temperature of just under 3 degrees above absolute zero. This discovery confirmed that the universe had indeed been much hotter and denser in the past. The detection of the cosmic microwave background was actually somewhat accidental. Two radio astronomers, Arno Penzias and Robert Wilson, were trying to eliminate a persistent noise from their antenna when they realized they had stumbled upon the echo of creation itself. No matter which direction they pointed their instrument, the mysterious radiation was always there, coming from every part of the sky with almost perfect uniformity. But the cosmic microwave background revealed something even more remarkable when scientists developed more sensitive instruments to study it. It was not perfectly smooth. Tiny variations in temperature, differences of just a few millionths of a degree, were scattered across the sky like fingerprints from the infant universe. These tiny ripples represented the seeds from which all structure in the universe would eventually grow. Regions that were slightly denser than average would attract more matter through gravity, eventually forming the first stars, galaxies, and galaxy clusters. These temperature fluctuations are so important that entire space missions have been dedicated to mapping them with ever greater precision. The Cosmic Background Explorer satellite in the 1990s first detected these variations. The Wilkinson Microwave Anisotropy Probe refined the measurements in the 2000s. Most recently, the Planck satellite has created the most detailed map of the cosmic microwave background ever produced, revealing the structure of the universe when it was just 380,000 years old. Modern telescopes have mapped these temperature fluctuations with extraordinary precision. The patterns we see match the predictions of Big Bang cosmology so perfectly that scientists can determine the age of the universe, its composition, and its geometry with remarkable accuracy. We know that ordinary matter, the stuff that makes up stars, planets, and people, makes up only about 5% of the total contents of the universe. Dark matter, which interacts gravitationally but not electromagnetically, accounts for about 27%. Dark energy, which drives the accelerating expansion of space, makes up the remaining 68%. This precise mapping of the cosmic microwave background has allowed cosmologists to test their theories with unprecedented accuracy. The universe appears to be geometrically flat, meaning that parallel lines remain parallel over cosmic distances. The expansion is accelerating, driven by some mysterious form of energy that permeates all of space. The ordinary matter we are familiar with is just a tiny fraction of what actually exists. Yet for all the success of Big Bang theory in explaining the evolution of the universe, it faces a fundamental limitation that brings us back to our central question about origins. The physics we understand breaks down as we try to trace cosmic history back to the very beginning. Our equations become meaningless at temperatures and densities so extreme that quantum effects and gravity both become important at the same scale. This breakdown occurs at what physicists call the Planck time, approximately 10 to the negative 43 seconds after the expansion began. To put this unimaginably brief instant in perspective, there are more Planck times in a single second than there have been seconds since the universe began. At this moment, the universe was so small that quantum uncertainty would have affected the very geometry of space and time. Our current theories simply cannot describe what happened before this point, or even whether the concept of before has any meaning. At the Planck scale, the smooth fabric of space-time that we experience in everyday life becomes a quantum foam of virtual particles and fluctuating geometry. The very notions of distance and duration lose their meaning. This is the frontier where our understanding currently ends, the wall beyond which our best theories cannot see. This is where the mystery deepens. The Big Bang Theory tells us that the universe expanded from an extremely hot, dense state, but it cannot tell us where that state came from or why it existed in the first place. It describes the evolution of the universe, but not its ultimate origin. To go further back, to understand the true beginning, we need new physics that can unite quantum mechanics with gravity in a consistent way. Some of the most brilliant theoretical physicists of our time are working on this problem. They have proposed theories like string theory and loop quantum gravity that might allow us to peer beyond the Planck time and understand what really happened at the moment of creation. But these theories remain largely untested and highly speculative, existing more in the realm of mathematical beauty than experimental verification. What we do know with confidence is that the universe has been expanding and cooling for nearly 14 billion years. We can trace this expansion back to a time when the entire observable universe was compressed into a space smaller than an atom. We can map the cosmic microwave background and see the imprints of quantum fluctuations that occurred in the earliest moments of cosmic history. We can observe the abundances of light elements and confirm that they match exactly what nuclear physics predicts for the first few minutes after the Big Bang. But this remarkable success in describing cosmic evolution only makes the ultimate question more pressing. If the Big Bang describes the expansion of space and time from this incredibly hot, dense state, where did that initial state come from? What existed before the Big Bang, and is it even meaningful to ask about a time before time began? What could have caused space and time themselves to spring into existence? These questions push us beyond the comfortable realm of observational astronomy and into the strange borderland where physics meets philosophy, where the very foundations of reality become the subject of investigation. The question seems so natural, so obvious, that we barely think twice about asking it. If the Big Bang was the beginning of our universe, what came before it? What was happening in the moments, years, or eons that preceded that initial expansion? But as we will discover, this apparently simple question leads us into some of the deepest mysteries of physics and challenges our most basic assumptions about the nature of time itself. According to Einstein's general theory of relativity, the framework that best describes gravity and the large-scale structure of the universe, time and space are not separate entities. They are woven together into a single fabric called space-time. This insight, revolutionary when Einstein first proposed it over a century ago, has profound implications for our understanding of cosmic origins. If the Big Bang represents the beginning of space, then it also represents the beginning of time. There is no universal clock ticking away in the background, no absolute time that existed before the universe began. Time itself is part of the physical universe, subject to the same laws and limitations as matter and energy. When space began to expand, time began to flow. Before that moment, the very concept of before loses its meaning. To understand this mind-bending idea, physicists often use an analogy. Imagine you are standing at the North Pole of Earth. You can walk in any direction, south, and you can ask meaningful questions about what lies to the south of where you stand. But if you ask what lies north of the North Pole, the question itself becomes meaningless. There is no north of the North Pole because north is defined in relation to the pole itself. Similarly, if time began with the Big Bang, asking what came before it is like asking what lies north of the North Pole. The question assumes something that may not exist, time and before are concepts that only have meaning within the context of an existing space-time. And if space-time itself began with the Big Bang, then there may simply be no before to discuss. This conclusion, radical as it seems, emerges naturally from our best understanding of gravity and cosmology. When Einstein's equations are applied to a universe filled with matter and energy, they describe a space-time that had a definite beginning. The mathematical models show a boundary beyond which the equations cannot be extended, an edge of time itself. But not all physicists are satisfied with this answer. The idea that time simply began, with nothing preceding it, strikes many as unsatisfying or incomplete. It seems to push the mystery back one level without really solving it. If the universe began from a hot, dense state, what caused that state to exist? What determined its properties? And perhaps most puzzling, what selected the particular laws of physics that govern its evolution? These questions have motivated physicists to explore alternative models of cosmic origins, scenarios in which our Big Bang might not represent the absolute beginning of everything, but rather a transition from some earlier phase of existence. These models are highly speculative, pushing the limits of theoretical physics, but they offer intriguing possibilities for what might have preceded our cosmic expansion. One class of models proposes that the universe undergoes cycles of expansion and contraction. In these bouncing cosmologies, our Big Bang might represent the rebound from a previous phase of cosmic collapse. Imagine the universe expanding for billions of years, then slowly decelerating, stopping, and beginning to contract. Eventually, it would collapse back down to an extremely dense state. But instead of forming a singularity where physics breaks down, quantum effects might cause it to bounce back, initiating a new phase of expansion. In this scenario, there could have been countless cycles before our current expansion began. Each cycle might last hundreds of billions of years, with universes expanding, contracting, and bouncing back in an eternal rhythm. Our Big Bang would then be just the most recent bounce in an infinite series, and the question of ultimate origins would be pushed back indefinitely. These cyclic models are appealing because they avoid the problem of a beginning altogether. If the universe has been bouncing for an infinite time, there is no need to explain where it came from or what caused it to exist. It simply always has been, cycling through phases of expansion and contraction in an endless dance of creation and destruction. But cyclic models face significant challenges. Each cycle would tend to produce more entropy, more disorder than the previous one. The universe would gradually become more chaotic and less structured with each bounce. Over infinite time, this process would lead to a completely disordered state, which is not what we observe. Our universe appears to have started in a remarkably ordered low entropy state, which seems difficult to explain if it emerged from the debris of a previous cosmic collapse. Another approach to the before question comes from string theory, one of the most ambitious attempts to unify quantum mechanics with gravity. In some versions of string theory, our familiar three-dimensional space might be just one slice of a higher dimensional reality. Our universe could exist on what physicists call a brane, short for membrane, floating in a higher dimensional space called the bulk. In these models, our Big Bang might have been triggered by a collision between our brane and another brane moving through the bulk. This collision would release enormous amounts of energy, heating up our brane and initiating the expansion we observe as the Big Bang. The colliding branes would then separate and move apart through the higher dimensional space until they collide again, potentially creating a new cycle of expansion. This brane world scenario, part of what cosmologists call the ekpyrotic universe model, offers another way to avoid the problem of an absolute beginning. The branes could have been colliding and separating for an infinite time, with each collision creating what appears to be a Big Bang from the perspective of observers living on one of the branes. Yet another possibility emerges from quantum mechanics, the theory that describes the behavior of matter and energy at the smallest scales. In quantum theory, empty space is not truly empty. It is filled with quantum fields that are constantly fluctuating, creating pairs of particles and antiparticles that appear briefly and then annihilate each other. These quantum fluctuations are not just theoretical curiosities. They have been measured in laboratory experiments and are responsible for subtle effects that confirm our understanding of quantum physics. Some physicists have suggested that our entire universe might have emerged from a quantum fluctuation in some pre-existing space. In this view, the Big Bang was not the beginning of everything, but rather the emergence of our particular region of space-time from a larger quantum vacuum. This vacuum would exist outside of time as we understand it, and universes could spontaneously appear within it, like bubbles forming in boiling water. This idea leads naturally to the concept of eternal inflation, a model in which new universes are constantly being created through quantum fluctuations in an ever-expanding multiverse. Our Big Bang would represent the birth of just one bubble universe among countless others, each with its own laws of physics and its own history. But even these exotic models do not fully resolve the before question. If our universe emerged from a quantum vacuum, where did that vacuum come from? If it was created by brane collisions, what determined the properties of the branes and the higher dimensional space they move through? If it resulted from a previous cosmic cycle, what started the cycles in the first place? Each attempt to explain what came before our Big Bang seems to require something that itself needs explanation. We find ourselves in a situation philosophers call infinite regress, where each answer raises new questions that demand their own answers. The search for the ultimate before threatens to go on forever, with each explanation requiring a deeper explanation. This is where some physicists have begun to question whether the concept of before is even applicable to the ultimate origins of reality. Perhaps the universe does not need a cause in the traditional sense. Perhaps existence is simply the default state, and nothingness is what would require explanation. This radical idea challenges our deepest intuitions about causation and existence, but it may be necessary if we are to make progress on the deepest questions about our origins. The honest answer to the question of what came before the Big Bang is that we do not know. We have intriguing models and speculative theories, but no definitive evidence for any particular scenario. The question pushes us to the very limits of scientific knowledge, and perhaps beyond, into realms where the traditional methods of physics may not apply. What we can say with confidence is that the question itself reveals something profound about the nature of scientific inquiry. Science excels at describing how things work and how they change, but it struggles with questions of ultimate origins and purposes. The more we learn about the universe, the more we realize how much we still do not understand about the deepest levels of reality. Before we can understand how something might come from nothing, we must first grapple with a question that seems almost childishly simple, yet turns out to be one of the most profound puzzles in all of philosophy and physics. What exactly do we mean by nothing? This question, which has occupied the minds of thinkers from ancient Greece to modern laboratories, reveals that nothing is far more complex and mysterious than we might initially suppose. When most people think of nothing, they imagine empty space, a vast, dark void stretching infinitely in all directions, devoid of matter, energy, sound, or light. This intuitive picture of nothingness has deep roots in human experience. We can empty a box of its contents and call it empty. We can pump the air out of a container and create what we call a vacuum. We can turn off all the lights in a room and experience darkness. These everyday experiences shape our understanding of what it means for something to be absent or empty. But as physics has progressed, This intuitive notion of nothing has proven to be inadequate and, in many ways, completely wrong. What we call empty space, what we think of as a perfect vacuum containing absolutely nothing, turns out to be one of the most active and energetic places in the entire universe. Far from being a passive backdrop against which the drama of existence plays out, empty space is itself a player in the cosmic story, filled with invisible fields and seething with constant activity. The first hint that empty space might not be truly empty came from quantum mechanics, the theory that describes the behavior of matter and energy at the smallest possible scales. According to quantum theory, the act of measurement itself affects what we are trying to measure, and there are fundamental limits to how precisely we can know certain properties of any system. This uncertainty is not due to imperfect instruments or inadequate techniques. It is built into the very fabric of reality itself. One of the most important consequences of quantum uncertainty is that energy cannot be perfectly zero, even in what we call empty space. The quantum vacuum, as physicists call it, must have what is known as zero-point energy. Even when we remove every particle, every wave, every detectable form of matter and energy from a region of space, quantum mechanics tells us that the fields that fill that space are still fluctuating with their minimum possible energy. These quantum fluctuations are not merely theoretical abstractions. They have real, measurable effects that have been confirmed in countless experiments. One of the most famous is the Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948. When two metal plates are placed very close together in a vacuum, they experience a small attractive force that pushes them together. This force arises because the quantum fluctuations of the electromagnetic field are slightly suppressed between the plates compared to the region outside them, creating a pressure difference that pushes the plates together. The Casimir effect has been measured with extraordinary precision in modern laboratories, confirming that empty space is indeed filled with quantum fluctuations. These measurements provide direct evidence that the vacuum is not empty in the way we normally think of emptiness. Instead, it is a dynamic, fluctuating medium that can exert forces on matter and influence the behavior of particles and fields. But the quantum vacuum is strange in ways that go far beyond simple fluctuations. According to quantum field theory, the framework that combines quantum mechanics with special relativity, the vacuum is constantly creating and destroying pairs of virtual particles. These particles appear out of the fluctuating fields, exist for incredibly brief moments, and then annihilate each other and disappear back into the vacuum. These virtual particles are not just mathematical conveniences or approximations. They have measurable effects on the properties of atoms and the behavior of light. They cause tiny shifts in the energy levels of hydrogen atoms, an effect called the Lamb shift that was first measured in 1947. They contribute to the magnetic properties of electrons and other particles. They affect the way light propagates through space and the rates at which excited atoms emit photons. The picture that emerges from quantum field theory is of a vacuum that is far from empty. It is a seething foam of virtual particles, constantly appearing and disappearing, borrowing energy from the uncertainty principle and paying it back before the cosmic accountants can notice. This quantum vacuum has structure, properties, and dynamics that are as real and important as those of ordinary matter. Yet even this quantum nothing, active and structured as it is, may not represent the deepest level of emptiness that we can conceive. The quantum vacuum still assumes the existence of space and time, of quantum fields and the laws that govern them. It presupposes a framework of physics within which the fluctuations can occur. But what if we try to imagine a nothing that is even more fundamental, a nothing that contains no space, no time, no fields, no laws, no mathematical structures, no potential for anything to exist. This is what philosophers call absolute nothingness, and it represents perhaps the most challenging concept that human minds have ever attempted to grasp. Absolute nothingness would contain no properties, no dimensions, no relationships, no information, no possibility of change or development. It would not be dark, because darkness implies the absence of light, which requires space and electromagnetic fields to have meaning. It would not be empty, because emptiness implies a container that could potentially be filled. Absolute nothingness would be the complete absence of existence itself. No space to contain anything, no time for processes to unfold, no laws to govern behavior, no principles to constrain possibilities. It would be a state, if we can even call it a state, in which the very concepts of existence and non-existence lose their meaning because there would be no framework within which to define them. Many philosophers have argued that absolute nothingness is not just difficult to understand, but is actually logically impossible. To think about absolute nothingness, they argue, is already to posit something, namely, the thinking about it. To describe absolute nothingness is to give it properties, which contradicts its supposed nature as having no properties. To conceive of absolute nothingness is to place it within the realm of concepts, which gives it a kind of existence, even if only as an idea. Some have gone further and suggested that absolute nothingness is not just logically problematic, but is actually unstable. If true nothingness could somehow exist, they argue, it would have no laws or constraints to prevent something from arising from it. In a sense, absolute nothingness would be so unconstrained that it could not maintain itself. The absence of any prohibition against existence might make existence inevitable. This leads us to one of the most startling ideas in modern physics and philosophy. Perhaps the question is not how something can come from nothing, but rather how nothing could possibly remain nothing. Perhaps existence is not an accident that needs to be explained, but the natural and inevitable state of affairs. Perhaps nothingness is what would be surprising and require explanation. This perspective turns our usual thinking about cosmic origins completely upside down. Instead of asking why there is something rather than nothing, we might ask why there should ever be nothing rather than something. Instead of seeking the cause that brought the universe into existence, we might wonder what could possibly prevent existence from being the default state of reality. But even if we accept that absolute nothingness might be impossible or unstable, this does not solve the mystery of cosmic origins. It simply rephrases the question: if nothingness is impossible, why does the universe have the particular properties it does? Why these laws of physics rather than others? Why this amount of matter and energy rather than more or less? Why this particular balance of forces that allows complexity and life to emerge? Different types of nothing lead to different possibilities for cosmic origins. If our universe emerged from a quantum vacuum, then it inherited the properties and constraints of quantum field theory. The laws of physics were already present in some form, waiting to shape the development of space, time, matter, and energy. If it emerged from absolute nothingness, then even the laws themselves had to arise from the absence of any constraint or structure. The question of what nothing really means takes us to the heart of some of the deepest problems in science and philosophy. It forces us to examine our assumptions about existence, causation, and the nature of reality itself. It reveals that even the absence of everything is not as simple or straightforward as it first appears. As we will see in the following chapters, the answer to what nothing means has profound implications for how we understand the origin of our universe. Whether we are talking about quantum vacuum, empty space-time, or absolute nothingness, determines what kinds of mechanisms might be responsible for the emergence of everything we observe around us. The nature of nothing shapes the nature of the something that might arise from it, and understanding this relationship is crucial to our quest to understand how the universe began from what appears to be its complete absence. Now that we understand that nothing is not truly empty, we can begin to explore one of the most remarkable ideas in modern physics. Could the entire universe, with all its galaxies, stars, planets, and the very space and time that contain them, have emerged from the quantum fluctuations of empty space? This possibility, which would have seemed like pure fantasy just a century ago, has become a serious scientific hypothesis that addresses the deepest questions about cosmic origins. The story begins with one of the most counterintuitive principles in all of physics, the Heisenberg uncertainty principle. Named after German physicist Werner Heisenberg, who formulated it in 1927, this principle states that there are fundamental limits to how precisely we can know certain pairs of properties of any quantum system. The more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa. This is not a limitation of our measuring instruments, but a fundamental feature of reality itself. But the uncertainty principle applies to more than just position and momentum. It also governs the relationship between energy and time. The principle tells us that for very short periods of time, energy can fluctuate by large amounts without violating any physical laws. The shorter the time interval, the larger the energy fluctuation that is allowed. This creates a cosmic loophole that has profound implications for our understanding of how something can arise from nothing. In the quantum world, this energy-time uncertainty manifests as the constant creation and annihilation of particle pairs in what we call the vacuum. Even in completely empty space, with no matter or radiation present, pairs of particles and antiparticles are constantly popping into existence, existing for incredibly brief moments, and then annihilating each other and disappearing back into the vacuum. These virtual particles, as they are called, live on borrowed energy from the uncertainty principle, and they must pay back this energy debt by annihilating before the cosmic enforcement mechanisms can catch them. The lifetimes of these virtual particles are unimaginably short. A virtual particle pair with the mass of an electron can exist for only about 10 to the negative 21 seconds before it must annihilate. More massive particles have even shorter lifetimes. A pair of virtual protons can exist for only about 10 to the negative 24 seconds. These durations are so brief that they make a single second seem like an eternity by comparison. Yet despite their fleeting existence, virtual particles have real and measurable effects on the physical world. They contribute to the magnetic properties of electrons, causing tiny deviations from the predictions of simpler theories. They affect the energy levels of atoms, producing small but detectable shifts in the colors of light that atoms emit and absorb. They influence the forces between particles and the rates of radioactive decay. In countless experiments, physicists have confirmed that these ghostly fluctuations of the vacuum are not mathematical abstractions, but genuine features of reality. The key insight that connects quantum fluctuations to cosmic origins came from the realization that if particles can be borrowed from the vacuum for short periods of time, perhaps entire regions of space and time can be borrowed as well. If the uncertainty principle allows large energy fluctuations for brief moments, could it allow the fluctuation of something as massive as a universe? At first glance, this seems impossible. The universe contains an enormous amount of matter and energy, far more than could ever be borrowed even for the briefest instant allowed by the uncertainty principle. The mass energy of all the observable matter in the universe is approximately 10 to the 53 kilograms worth of energy. According to the uncertainty principle, borrowing this much energy would require paying it back in a time shorter than 10 to the negative 104 seconds, an interval so brief that it defies comprehension. But here is where the story takes a remarkable turn. While the universe contains an enormous amount of positive energy in the form of matter and radiation, it also contains an enormous amount of negative energy in the form of gravitational potential energy. every pair of particles in the universe is gravitationally attracted to every other pair, and this universal attraction represents a form of negative energy that partially cancels out the positive energy of matter. Some physicists have calculated that when all forms of energy are properly accounted for, including the positive energy of matter and radiation and the negative energy of gravitational attraction, the total energy of the universe might be exactly zero. If this is correct, then the entire universe could be a quantum fluctuation that borrowed zero net energy from the vacuum and therefore never needs to pay it back. This idea, sometimes called the zero energy universe hypothesis, suggests that our cosmos is the ultimate free lunch. The universe created itself through a quantum fluctuation that cost nothing because the books balance perfectly. The positive energy of matter and the negative energy of gravity cancelled each other out exactly, allowing the fluctuation to persist indefinitely without violating the conservation of energy. But even if the total energy of the universe is zero, this does not immediately solve the problem of cosmic origins. The uncertainty principle would still seem to limit the size of any quantum fluctuation. A fluctuation large enough to contain our entire observable universe would seem to require repayment in an impossibly short time, regardless of whether the total energy borrowed was zero. This is where the concept of cosmic inflation becomes crucial to the story. Inflation, as we will explore in detail in the next chapter, is a period of exponential expansion that could have occurred in the earliest moments of cosmic history. During inflation, space itself expanded faster than the speed of light, stretching tiny quantum fluctuations to cosmic proportions in an incredibly brief time. If inflation occurred, then our entire observable universe could have emerged from a quantum fluctuation no larger than a subatomic particle. This tiny fluctuation, well within the bounds allowed by the uncertainty principle, could have been stretched by inflation to encompass everything we can see today. The mechanism that allows something to come from nothing would not be a single giant fluctuation, but rather a tiny fluctuation, amplified to cosmic size by the exponential expansion of space itself. This scenario leads to an even more remarkable possibility called eternal inflation. If quantum fluctuations can create regions of inflating space, and if inflation can stretch these regions to enormous size, then the process might continue indefinitely. Each inflating region could spawn new inflating regions through additional quantum fluctuations, creating an infinite branching tree of universes, each growing exponentially and giving birth to new universes in turn. In this picture, our universe would be just one bubble in an infinite foam of universes, all arising from quantum fluctuations in an eternally inflating multiverse. The process would have no beginning and no end, with new universes constantly being born from the quantum activity of empty space. The question of how something came from nothing would be replaced by the realization that the something was always there, constantly creating more of itself through the inherent instability of the quantum vacuum. Yet even this remarkable scenario does not fully resolve the mystery of origins. The eternal inflation hypothesis still assumes the existence of quantum fields, the laws of quantum mechanics, and the mechanism of inflation itself. It pushes the question back one level, but does not eliminate it entirely. We still need to explain where the quantum fields came from, why they have the properties they do, and what selected the particular laws of physics that govern their behavior. Some physicists have proposed even more radical possibilities. Perhaps the laws of physics themselves can fluctuate, emerging temporarily from a deeper level of reality that contains no fixed laws at all. In this view, our universe with its particular physical constants and fundamental forces would be just one possibility among countless others, selected not by design but by the random process of quantum fluctuation from a realm beyond physics itself. Others have suggested that the quantum fluctuations we observe might be reflections of even deeper mathematical structures. In this view, the universe exists because certain mathematical relationships are inherently more stable or more likely than others. The quantum vacuum with its fluctuating fields would emerge naturally from the underlying mathematical fabric of reality, and universes would arise wherever the mathematics allows or requires them to exist. These ideas push us to the very edge of scientific speculation and into the realm where physics begins to merge with philosophy and mathematics. They suggest that the ultimate foundation of reality might not be particles or fields or even space and time, but rather abstract mathematical principles that generate physical existence as a kind of side effect of their own internal logic. The quantum fluctuation origin story is compelling because it uses well-established principles of physics to address the deepest questions about existence. Virtual particles are real and measurable. Quantum fluctuations have been confirmed in countless experiments. The uncertainty principle is one of the most thoroughly tested ideas in all of science. If these principles can explain how particles appear from empty space, perhaps they can also explain how universes appear from nothing. But the story also reveals the limits of our current understanding. Each explanation requires assumptions about deeper levels of reality that themselves require explanation. The quantum fields that fluctuate must come from somewhere. The laws that govern their behavior must have some origin. The mathematical structures that might underlie everything must themselves exist in some sense, raising new questions about the nature of mathematical reality. As we continue our exploration of cosmic origins, we will see how the idea of quantum fluctuations connects with other profound concepts like cosmic inflation and the multiverse. We will discover how these ideas might explain not just the existence of our universe, but also its particular properties and the remarkable fact that it allows the emergence of complexity, structure, and life. The story of quantum fluctuations is just the beginning of an even more remarkable tale about how everything we see around us might have emerged from the inherent creativity of empty space itself. In our quest to understand how the universe could emerge from nothing, we now encounter one of the most revolutionary ideas in modern cosmology. Cosmic inflation, a period of exponential expansion that may have occurred in the first fraction of a second after the Big Bang, not only helps explain many puzzling features of our universe, but also provides a mechanism by which quantum fluctuations could grow from subatomic scales to cosmic proportions. This remarkable theory suggests that everything we see around us, from the smallest atoms to the largest galaxy clusters, began as tiny ripples in the fabric of space itself. The story of cosmic inflation begins with a series of problems that plagued cosmologists in the late 20th century. The Big Bang theory was extraordinarily successful at explaining the overall expansion of the universe, the formation of light elements, and the existence of the cosmic microwave background radiation. But as observations became more precise, several puzzling features emerged that seemed difficult to explain within the standard framework. The first puzzle was known as the horizon problem. When we look at the cosmic microwave background radiation, we see that it has almost exactly the same temperature in every direction we observe. The variations are tiny, only a few parts per 100,000. This uniformity is remarkable, but according to the standard Big Bang model, it should be impossible. The problem is that regions of the sky that are separated by more than about 2 degrees have never been in contact with each other. Light from these regions has not had enough time since the Big Bang to travel between them and equilibrate their temperatures. Yet somehow, these causally disconnected regions of space have almost identical temperatures. How could regions that have never communicated with each other have reached such precise thermal equilibrium? The second puzzle was the flatness problem. The geometry of space can be curved in various ways, just as the surface of Earth is curved, even though it appears flat to us locally. Space can have positive curvature, like the surface of a sphere, negative curvature, like a saddle, or it can be perfectly flat, like an infinite plane. observations suggest that our universe is very close to being geometrically flat, perhaps exactly flat. But according to the standard Big Bang model, achieving this flatness would require incredibly precise fine-tuning of the initial conditions. If the universe had started with even slightly too much matter and energy, it would have curved space positively and collapsed back on itself long before stars and galaxies could form. If it had started with even slightly too little, space would have curved negatively and expanded so rapidly that matter could never have clumped together to form structures. The amount of fine-tuning required is staggering. The initial density of the universe would have needed to be adjusted to within 1 part in 10 to the 60th of the critical value to produce the flat universe we observe today. This level of precision is like balancing a pencil on its point for billions of years without it falling over. While not impossible, it seemed to require an explanation. The third puzzle was the monopole problem. Many theories that attempt to unify the fundamental forces of physics predict the existence of exotic particles called magnetic monopoles. These would be particles that act like isolated north or south magnetic poles, unlike ordinary magnets, which always have both north and south poles together. If these theories are correct, the Big Bang should have produced enormous numbers of these monopoles, and they should be easy to detect today. Yet despite extensive searches, no magnetic monopoles have ever been found. These 3 problems, the horizon problem, the flatness problem, and the monopole problem, suggested that something important was missing from the standard Big Bang picture. The solution came from a young physicist named Alan Guth, who in 1980 proposed a radical modification to the early history of the universe. Guth suggested that in the earliest moments after the Big Bang, the universe underwent a period of exponential expansion, unlike anything in its later history. During this inflationary epoch, space expanded faster than the speed of light, doubling in size every tiny fraction of a second. In less than 10 to the negative 32 seconds, a region smaller than a proton could expand to the size of a grapefruit or larger. This exponential expansion would solve all 3 problems simultaneously. The horizon problem would be resolved because regions that appear disconnected today were actually in close contact before inflation began. They had time to reach thermal equilibrium when they were close together, and then inflation stretched them apart to cosmic distances while preserving their common temperature. The flatness problem would be solved because inflation stretches space so dramatically that any initial curvature becomes negligible. Just as the surface of Earth appears flat to us even though we know it is curved, inflation would make space appear flat on all observable scales, regardless of its initial geometry. Any original curvature would be stretched to scales far larger than anything we can observe. The monopole problem would be resolved because inflation would dilute the density of any exotic particles produced in the Big Bang to undetectable levels. If monopoles were created before inflation, they would be spread so thinly by the exponential expansion that we would be unlikely to find any in our observable universe. But inflation does much more than solve these technical problems. It provides a mechanism for generating the seeds of all cosmic structure. During the inflationary epoch, quantum fluctuations in the fields driving the expansion would be stretched from microscopic to macroscopic scales. These fluctuations would create tiny variations in the density of matter and energy that would later grow under the influence of gravity to become galaxies, stars, and planets. The process works like this. In the quantum vacuum, fields are constantly fluctuating on the smallest scales due to the uncertainty principle. Normally, these fluctuations average out over any macroscopic region and have no observable effect. But during inflation, these quantum fluctuations get frozen into the expanding fabric of space itself. As space stretches exponentially, fluctuations that began smaller than atoms grow to sizes larger than galaxies. These stretched quantum fluctuations become variations in the energy density of different regions of space. Some regions have slightly more energy, others have slightly less. After inflation ends and the universe begins its more familiar expansion, these energy variations translate into density variations in matter and radiation. Regions with higher energy density attract more matter through gravity, eventually forming the dense cores around which galaxies and galaxy clusters assemble. This connection between quantum fluctuations and cosmic structure is one of the most remarkable predictions of inflation theory. The tiny, random quantum jiggles that occur in empty space become the seeds of all the complexity we see in the universe today. Every galaxy, every star, every planet, and ultimately every atom in our bodies can trace its origins back to quantum fluctuations that occurred during the inflationary epoch. The predictions of inflation theory have been tested through detailed observations of the cosmic microwave background radiation. The patterns of temperature variations in this ancient light match precisely what inflation theory predicts for quantum fluctuations stretched to cosmic scales. The amplitude, the angular distribution, and the statistical properties of these fluctuations all agree with the theoretical expectations. More remarkably, inflation theory predicted specific relationships between different types of fluctuations that have been confirmed by observations. It predicted that the fluctuations should be nearly scale invariant, meaning they should have similar amplitudes on different size scales. It predicted that they should follow a Gaussian distribution, with most fluctuations being small and only rare fluctuations being large. It predicted that they should be adiabatic, meaning that all forms of matter and energy should fluctuate together in the same proportions. All of these predictions have been verified to extraordinary precision by satellite missions dedicated to mapping the cosmic microwave background. The Wilkinson Microwave Anisotropy Probe and the Planck satellite have measured the patterns of ancient light with such accuracy that cosmologists can test inflation theory at the level of a few percent or better. But perhaps the most profound implication of inflation theory is that it suggests our observable universe may be just a tiny part of a much larger reality. If inflation can occur once, it can occur multiple times. If quantum fluctuations can create one inflating region, they can create many inflating regions. This leads to the concept of eternal inflation, in which new universes are constantly being born from quantum fluctuations in regions of space that are still inflating. In this picture, inflation never really ends globally, even though it may end in particular regions like our observable universe. Instead, it continues forever, with some regions stopping their exponential expansion and evolving into universes like ours, while other regions continue inflating and spawning new universes through additional quantum fluctuations. This eternal inflation scenario leads to a multiverse of staggering proportions. There would be an infinite number of universes, each arising from its own quantum fluctuation, and each potentially having different physical properties. Some universes might have different fundamental constants, different numbers of dimensions, or different laws of physics altogether. Our universe would be just one member of this infinite ensemble, selected by the mere fact that its properties allow observers like us to exist. The field that drives inflation, often called the inflaton field, remains mysterious. We do not know what this field is made of, how it relates to other known particles and forces, or what mechanism causes it to behave in the way required for inflation. Several candidate fields have been proposed, ranging from completely new scalar fields to modifications of known fields, like the Higgs field, that gives mass to other particles. Despite these uncertainties, inflation has become the leading theory for the early universe because it explains so many otherwise puzzling features of our cosmos. It resolves the horizon, flatness, and monopole problems. It provides a mechanism for generating cosmic structure from quantum fluctuations. It makes specific, testable predictions that have been confirmed by observations. and it offers a natural explanation for how a universe could emerge from essentially nothing through the amplification of quantum vacuum fluctuations. Yet inflation also raises new questions that push us toward even deeper mysteries. What determined the properties of the inflaton field? What caused inflation to begin in the first place? What selected the particular vacuum state from which our universe inflated? And perhaps most fundamentally, what exists in the larger multiverse beyond our own cosmic bubble? These questions connect inflation theory to some of the most speculative ideas in modern physics and cosmology. They suggest that our universe may be embedded in a higher dimensional reality, with properties we can barely imagine. They hint at connections between cosmic origins and the deepest principles of quantum mechanics and geometry. And they raise the possibility that the ultimate explanation for our existence may lie not in any single universe, but in the infinite creativity of the quantum vacuum itself. Armed with our understanding of quantum fluctuations and cosmic inflation, we can now explore the specific scientific models that attempt to explain how our entire universe might have emerged from nothing. These theories represent some of the most ambitious and speculative ideas in modern physics, pushing the boundaries of human knowledge to their absolute limits. They combine quantum mechanics, general relativity, and exotic mathematical concepts to address the ultimate question of existence itself. The first and perhaps most influential of these models was proposed by Russian-American physicist Alexander Vilenkin in the early 1980s. Vilenkin's tunneling universe model draws on one of the strangest phenomena in quantum mechanics: the ability of particles to tunnel through energy barriers that would be impossible to cross according to classical physics. In the quantum world, particles can sometimes appear on the other side of an energy barrier without having enough energy to go over the top. This process, called quantum tunneling, occurs because quantum particles do not follow definite paths like classical objects. Instead, they exist as probability waves that can extend into regions that would be classically forbidden. While the probability of tunneling decreases exponentially with the height and width of the barrier, it never becomes exactly zero. Quantum tunneling is not merely a theoretical curiosity, it is responsible for the nuclear fusion that powers the sun, allows certain types of radioactive decay to occur, and makes possible the operation of many electronic devices, including the scanning tunneling microscope. Without quantum tunneling, stars would not shine, atoms would be stable in ways that would prevent chemistry, and much of modern technology would be impossible. Vilenkin proposed that the entire universe might have tunneled into existence from a state of absolute nothingness. In this model, nothingness is represented as a quantum state with zero energy, zero size, and no physical properties whatsoever. The universe we observe would correspond to a state with positive energy, finite size, and rich physical structure. Normally, the transition from nothing to something would require an enormous input of energy, creating an insurmountable barrier. But according to Vilenkin's calculations, when quantum mechanics and general relativity are combined properly, this energy barrier has a very special property. While it appears infinitely high from the perspective of classical physics, quantum mechanics allows the universe to tunnel through it with a small but finite probability. The universe could spontaneously appear from absolute nothingness without violating any physical laws. The key insight in Vilenkin's model is that the universe begins not with a Big Bang, but with a Big Bang preceded by a quantum tunneling event. The tunneling creates a tiny universe, perhaps smaller than a subatomic particle, that immediately begins to inflate exponentially. This inflation stretches the tiny universe to macroscopic size and fills it with the matter and energy we observe today. What makes this scenario particularly elegant is that it requires no pre-existing space, time, or physical laws. The tunneling event creates space and time along with matter and energy. The laws of physics emerge as the universe tunnels into existence rather than being imposed from outside. In a sense, the universe creates itself through the sheer possibility of its own existence. A related but distinct approach was developed by Stephen Hawking and James Hartley in the 1980s. Their no-boundary proposal takes a radically different approach to the problem of cosmic origins by eliminating the concept of a beginning altogether. Instead of asking what came before the Big Bang, they ask what happens when we trace the history of the universe back to its earliest moments using the principles of quantum mechanics. In the Hartley-Hawking model, time itself becomes imaginary in the mathematical sense as we approach the moment of the Big Bang. This might sound like mere mathematical trickery, but it has profound physical implications. When time becomes imaginary, the distinction between time and space disappears. The universe has no definite beginning in time, because time gradually transforms into space as we go backward toward the Big Bang. To understand this concept, Hawking often used the analogy of Earth's surface. If you travel north from any point on Earth, you will eventually reach the North Pole. But there is nothing north of the North Pole. The question what lies north of the North Pole is meaningless because north is defined relative to the pole itself. Similarly, in the Hartley-Hawking model, there is no moment before the Big Bang because time itself begins at the Big Bang. The mathematics of the no-boundary proposal describes the universe as emerging from a quantum superposition of all possible histories. Instead of having a single definite past, the universe exists in a quantum state that encompasses all possible ways it could have begun. The specific history we observe emerges from this superposition through the process of quantum measurement and decoherence. What makes the Hartley-Hawking model particularly intriguing is that it suggests the universe has no boundary in space-time. Just as Earth's surface has no edge even though it is finite in size, the universe's space-time has no boundary even though it may be finite in duration. The universe is self-contained, requiring no external cause or creator to bring it into existence. Both the Vilenkin tunneling model and the Hartley-Hawking no-boundary proposal rely on the idea that the universe has zero total energy. This concept, which we encountered in our discussion of quantum fluctuations, is crucial to making these models work. If the universe had positive total energy, its creation would violate the conservation of energy. If it had negative total energy, it would be unstable and would collapse immediately. But if the total energy is exactly zero, with the positive energy of matter and radiation precisely balanced by the negative energy of gravitational attraction, then the universe could emerge from nothing without violating any conservation laws. The universe would be, in the words of physicist Alan Guth, the ultimate free lunch. Calculating the total energy of the universe is extraordinarily difficult because it requires adding up all forms of energy, including some that are not well understood. The positive contributions include the rest mass energy of all particles, the kinetic energy of their motion, and the energy stored in electromagnetic and other fields. The negative contributions include the gravitational potential energy that arises from the mutual attraction of all particles. Recent estimates suggest that these positive and negative contributions may indeed cancel out to a very high degree of precision. While we cannot yet determine whether the total is exactly zero, it appears to be very close to zero, perhaps close enough to allow the universe to have emerged from nothing through quantum processes. Another important model for cosmic origins is the pre-Big Bang scenario, developed by Gabriele Veneziano and others in the context of string theory. String theory, which attempts to unify all fundamental forces including gravity, suggests that the basic building blocks of reality are not point particles, but tiny vibrating strings existing in higher dimensional spaces. In the pre-Big Bang model, our universe emerges from a collision between higher dimensional objects called branes, short for membranes. These branes exist in a higher dimensional space called the bulk, and they can move through this space like sheets of paper floating in air. When two branes collide, the enormous energy of the collision heats up the branes and creates the hot, dense state that we observe as the Big Bang. This scenario, part of what cosmologists call the ekpyrotic universe model, suggests that what we call the Big Bang was not the beginning of everything, but rather a violent transition from a pre-existing state. The collision between brains would create the matter and energy we observe while also initiating the expansion of space that we call cosmic inflation. The pre-Big Bang scenario has the advantage of avoiding the problem of creation from absolute nothingness by proposing that something, namely the brains and the higher dimensional space they move through, always existed, but it raises new questions about the origin of these pre-existing structures and the laws that govern their behavior. All of these scientific models for cosmic origins share certain common features. They all rely on quantum mechanics to provide the fundamental randomness and uncertainty that allows something to emerge from nothing. They all invoke some form of gravitational or geometric effect to balance the energy books and avoid violating conservation laws. And they all push the boundaries of known physics into realms where our current theories may not apply. Perhaps most importantly, these models all suggest that the question of why there is something rather than nothing may be based on a false premise. They propose that nothingness may be unstable, impossible, or meaningless, and that the existence of something may be the natural state of affairs, rather than a puzzle that requires explanation. The Vilenkin tunneling model suggests that absolute nothingness cannot maintain itself, because quantum mechanics provides a mechanism for universes to tunnel into existence. The Hartley-Hawking model suggests that the question of what came before the universe is meaningless, because time itself begins with the universe. The pre-Big Bang scenario suggests that the apparent beginning of our universe is actually a transition within a larger, eternally existing reality. Yet, all of these models remain highly speculative. They make predictions that are difficult or impossible to test with current technology. They rely on mathematical extrapolations of known physics into regimes where those physics may break down. And they often require the existence of exotic phenomena like higher dimensional spaces or imaginary time that have never been directly observed. Moreover, each model raises new questions that may be as difficult to answer as the original puzzle of cosmic origins. If the universe tunneled from nothingness, what determined the probability of tunneling and the properties of the resulting universe? If the universe has no boundary in time, what selected the particular quantum state from which it emerged? If our universe arose from brain collisions, what governs the behavior of brains and the higher dimensional spaces they inhabit? These questions suggest that the problem of cosmic origins may be like an infinite regress, with each answer leading to new questions that require their own explanations. Perhaps the ultimate answer lies not in any particular scientific model, but in a deeper understanding of the relationship between mathematics, physics, and existence itself. As we delve deeper into the mystery of cosmic origins, we encounter perhaps the most mind-expanding concept in all of modern cosmology. What if our universe, with its 13.8 billion-year history and its 100 billion galaxies, is not unique? What if it is just one member of an infinite collection of universes, each with its own properties, its own laws of physics, and its own story of cosmic evolution? This possibility, known as the multiverse, emerges naturally from many of the theories we have explored and offers a radically new perspective on the question of how something can come from nothing. The multiverse is not a single theory, but rather a consequence that emerges from several independent lines of theoretical investigation. Eternal inflation, quantum mechanics, string theory, and even certain interpretations of cosmological observations all point toward the existence of multiple universes beyond our own. While the details differ, these various approaches converge on the remarkable conclusion that our observable universe may be just a tiny fragment of a vastly larger reality. The first and most compelling route to the multiverse comes from eternal inflation, the extension of cosmic inflation theory that we explored in the previous chapter. Recall that inflation is driven by a special field, the inflaton field, that causes space to expand exponentially. In most regions of space, this inflation eventually ends, allowing the formation of matter, radiation, and the familiar structures we see in our universe. But here is the crucial insight that leads to eternal inflation. While inflation ends in some regions, quantum fluctuations ensure that it continues in others. The inflaton field is subject to the same quantum uncertainty that affects all fields in physics. These quantum fluctuations can sometimes cause the field to increase in value rather than decrease, extending the period of inflation in those regions. The result is a fractal-like structure of cosmic evolution. Some regions of space stop inflating and evolve into universes like ours, but other regions continue to inflate, doubling in size every tiny fraction of a second. Within these still inflating regions, new quantum fluctuations create patches that stop inflating, forming new universes, while other patches continue the exponential expansion. This process has no natural stopping point. Once it begins, eternal inflation continues forever, constantly creating new universes within an ever-expanding network of inflating space. The multiverse grows without bound, with an infinite number of universes being born at every moment. Each universe represents a different outcome of the quantum processes that occurred during its formation. The scale of this eternal inflation multiverse defies human comprehension. In any finite time, an infinite number of universes come into existence. Each universe can be enormous, potentially much larger than our own observable universe. The total volume of space increases without limit, providing an inexhaustible arena for cosmic creativity. But eternal inflation leads to an even more remarkable consequence. If there are infinitely many universes being created through random quantum processes, then every possible outcome that is not explicitly forbidden by the laws of physics must occur somewhere in the multiverse. This includes not just different amounts of matter and energy, but potentially different physical constants, different numbers of spatial dimensions, and even different fundamental laws of physics. The implications are staggering. Somewhere in the eternal inflation multiverse, there would be universes where the force of gravity is stronger or weaker than in ours. There would be universes where the electromagnetic force has different strength, where particles have different masses, where the speed of light has different values. There would be universes with different numbers of dimensions, different types of particles, and different rules governing their interactions. Most of these universes would be sterile, unable to support the formation of stars, planets, or any kind of complexity. A universe with gravity too strong would collapse before stars could form. A universe with gravity too weak would never allow matter to clump together into cosmic structures. A universe with electromagnetic forces that are too different would not permit the formation of stable atoms or molecules. But among the infinite variety of universes, some would have properties very similar to ours. Some would have exactly the right balance of forces to allow the formation of stars, planets, and perhaps even life. In fact, if the multiverse is truly infinite, there would be infinitely many universes with properties similar to ours, including universes that are virtually identical to ours in every detail. This leads to what cosmologists call the anthropic principle. We observe our universe to have the particular properties it does not, because those properties are inevitable or specially designed. But because we exist in a universe where those properties allow observers like us to exist. The apparent fine-tuning of physical constants for the existence of life is explained not by design but by selection. We observe a life-friendly universe because only life-friendly universes can be observed by living beings. The anthropic principle provides a potential solution to one of the deepest puzzles in cosmology and particle physics. Many of the fundamental constants of nature appear to be precisely tuned to allow the existence of stars, planets, atoms, molecules, and ultimately, life itself. If the strength of gravity was slightly different, if the mass of the proton was slightly larger or smaller, if the fine structure constant that governs electromagnetic interactions had a different value, the universe would be a very different and much less interesting place. In a single universe, this fine-tuning seems to require explanation. Why do the constants have exactly the values needed for complexity and life? But in a multiverse, with infinite variety, the question becomes moot. Among infinitely many universes with different constants, some will inevitably have the right values. We find ourselves in one of those rare universes simply because that is the only type of universe where observers can exist to wonder about cosmic fine-tuning. String theory, the ambitious attempt to unify all fundamental forces, including gravity, provides another route to the multiverse. String theory requires the existence of extra-spatial dimensions beyond the three we experience in everyday life. These extra dimensions must be curled up or compactified in some way to remain hidden from direct observation. But there are many different ways that extra dimensions can be compactified, and each different configuration leads to different physics in the familiar three-dimensional world. String theorists have identified something called the string landscape, a vast collection of different possible configurations for the extra dimensions. Each point in this landscape corresponds to a different possible universe with different physical properties. The number of possibilities in the string landscape is enormous, perhaps as large as 10 to the 500th power or even larger. This creates what string theorists call a landscape of vacua, different ground states of the string theory equations that correspond to different possible universes. Our universe would occupy just one tiny region of this vast landscape, with different regions corresponding to universes with different properties. If eternal inflation operates within the context of string theory, then different regions of the multiverse could explore different parts of the string landscape. Quantum fluctuations during inflation could cause transitions between different vacuum states, creating universes with different compactifications of the extra dimensions, and therefore different physics. This combination of eternal inflation and string theory leads to a multiverse of almost unimaginable diversity. Not only would there be infinitely many universes, but these universes could have fundamentally different laws of physics. Some might have different numbers of forces, different types of particles, or even different logical structures governing physical processes. Yet another type of multiverse emerges from certain interpretations of quantum mechanics itself. The many worlds interpretation proposed by Hugh Everett III in 1957 suggests that every quantum measurement or interaction causes the universe to split into multiple parallel branches. Each branch corresponds to a different possible outcome of the quantum process. In this many worlds multiverse, every time a particle can decay or not decay, every time a quantum measurement can yield one result or another, the universe branches into separate realities that explore all possibilities simultaneously. The result is an exponentially growing tree of parallel universes, each representing a different sequence of quantum outcomes. While the many worlds interpretation remains controversial among physicists, it offers yet another perspective on the multiverse concept. It suggests that the randomness we observe in quantum mechanics is not fundamental, but rather reflects our ignorance of which branch of the universal wave function we happen to inhabit. The multiverse concept also emerges from attempts to understand the mathematical structure of reality itself. Some physicists and philosophers have proposed that all mathematically consistent structures exist in some sense, and that physical universes correspond to particular mathematical frameworks. In this view, our universe exists because the mathematics that describes it is self-consistent, and other universes exist corresponding to other mathematical structures. This mathematical multiverse would be the largest of all. encompassing not just different physical constants or laws, but different logical and mathematical foundations for reality itself. Universes might exist where mathematics itself operates according to different rules, where the relationship between mathematical structures and physical existence follows different principles. Despite the compelling theoretical motivations for the multiverse, the concept faces significant challenges and criticisms. The most fundamental problem is that other universes, by definition, lie beyond our ability to observe or interact with them. This makes the multiverse hypothesis difficult or impossible to test using traditional scientific methods. Critics argue that if a theory cannot be tested or falsified, it is not truly scientific, but rather belongs to the realm of philosophy or speculation. They point out that the multiverse seems to explain everything and therefore predicts nothing, making it an empty concept that cannot guide further research or understanding. Proponents respond that the multiverse is not a theory in itself, but rather a consequence of other theories that can be tested. Eternal inflation makes specific predictions about the cosmic microwave background radiation. String theory makes predictions about particle physics that may be testable at high-energy accelerators. Quantum mechanics makes countless testable predictions about the behavior of matter and energy. Moreover, some aspects of the multiverse might be indirectly testable. If eternal inflation is correct, we might find evidence of collisions between our universe and neighboring universes in the form of unusual patterns in the cosmic microwave background. If the many worlds interpretation is correct, we might find ways to detect quantum interference effects between different branches of reality. The multiverse also raises profound philosophical questions about the nature of existence, probability, and explanation. If there are infinitely many universes with infinitely many possible properties, what does it mean to say that something is probable or improbable? How do we assign meaning to scientific laws if they are just local regularities that vary from universe to universe? Perhaps most unsettling, the multiverse seems to undermine the specialness of our own existence. If there are infinitely many universes, including infinitely many with properties very similar to ours, then our particular cosmic story becomes just one among infinitely many similar stories. The Earth, the solar system, human civilization, and even our individual lives lose their uniqueness in the face of infinite repetition across the multiverse. Yet the multiverse also offers a kind of cosmic optimism. If there are infinitely many universes exploring all possibilities, then somewhere in the vast expanse of reality, every dream is realized, every possibility is explored, every potential is actualized. The multiverse becomes an infinite canvas for creativity and existence, ensuring that nothing that can be will fail to be somewhere and somewhen. The multiverse concept represents the ultimate extension of the Copernican revolution. Just as Copernicus showed that Earth is not the center of the solar system, and just as later, astronomers showed that our solar system is not the center of the galaxy, and our galaxy is not the center of the universe, the multiverse suggests that our entire universe is not the center of reality. We inhabit a vast, perhaps infinite ensemble of universes, each as real and significant as our own. Whether the multiverse exists remains one of the great open questions in cosmology and fundamental physics. But the mere possibility forces us to reconsider our most basic assumptions about existence, uniqueness, and our place in the grand scheme of things. It suggests that the question of how something came from nothing may have infinitely many answers, one for each universe in the endless multiverse that quantum creativity continues to bring into being. As we have explored the various theories for how the universe might have emerged from nothing, a deeper question has gradually emerged from the shadows. All of our scientific models, from quantum tunneling to eternal inflation to brain collisions, assume the existence of physical laws that govern these processes. Quantum mechanics provides the rules for tunneling, general relativity describes the geometry of space-time, and field theory explains how inflation works. But this raises a profound puzzle that strikes at the very heart of our quest to understand cosmic origins. If the universe came from nothing, where did the laws of physics themselves come from? This question forces us to confront the deepest foundations of scientific understanding. Throughout history, physicists have discovered mathematical relationships that describe how the universe behaves. Newton found equations that govern the motion of planets and projectiles. Maxwell discovered equations that unify electricity and magnetism. Einstein revealed equations that connect space, time, matter, and energy. Schrödinger and Heisenberg developed equations that describe the quantum world. These equations are not merely human inventions or convenient approximations. They appear to capture something fundamental about the structure of reality itself. When we solve Einstein's equations for the evolution of the universe, we get predictions that match observations with extraordinary precision. When we use quantum field theory to calculate the properties of particles, we get results that agree with experiments to more than 10 decimal places. The effectiveness of mathematics in describing the physical world is so remarkable that physicist Eugene Wigner called it an unreasonable effectiveness. Why should abstract mathematical concepts invented by human minds correspond so perfectly to the workings of the natural world? Why should the universe be mathematical at all? And why should it follow consistent rules that can be expressed in elegant equations? This mystery becomes even more profound when we consider cosmic origins. If the universe began from nothing, did it create the laws of physics as it came into being? Or did the laws somehow exist before the universe, waiting to govern its birth and evolution? The first option seems to require the universe to pull itself up by its own bootstraps, creating the very rules that allowed its creation. The second option seems to require the pre-existence of abstract mathematical structures in some realm outside physical reality. To understand this puzzle, we must first examine what we mean by laws of physics. At the most basic level, these laws are mathematical relationships that describe patterns in the behavior of matter and energy. They tell us that certain quantities are conserved, that certain symmetries are respected, and that certain processes can occur while others cannot. They provide the framework within which all physical events unfold. But are these laws discovered or invented? Do they exist independently of the physical universe, or are they emergent properties of the universe itself? This question has divided physicists and philosophers for centuries, and it becomes particularly acute when we consider how the laws might have originated along with the universe itself. One possibility is that the laws of physics are emergent properties that arise naturally from the most basic features of existence. In this view, the laws are not imposed on the universe from outside, but rather develop as necessary consequences of the fact that something exists rather than nothing. The mathematical relationships we observe might be the only consistent ways that a universe can behave once it begins to exist. This emergent perspective suggests that the laws of physics are like the rules of logic. Just as logical principles such as the law of non-contradiction seem to be necessary features of any coherent system of thought, the laws of physics might be necessary features of any coherent system of existence. A universe without conservation laws, without consistent relationships between cause and effect, without mathematical structure, might simply be impossible or meaningless. Support for this view comes from the deep connections that physicists have discovered between different physical laws. The laws of thermodynamics emerge from the statistical behavior of large numbers of particles. The conservation of energy follows from the symmetry of physical laws with respect to time translation. The conservation of electric charge follows from a different kind of symmetry in the equations of electromagnetism. These connections suggest that the laws of physics form an integrated web of relationships, each law connected to and dependent on the others. This web might be so tightly constrained that only one self-consistent set of laws is possible. In this view, the laws of physics exist because they are the only laws that could exist, and the universe obeys them because there is no alternative. Another possibility is that the laws of physics are more fundamental than the physical universe itself. In this view, mathematical structures and relationships exist in some abstract realm, independent of space, time, matter, and energy. The physical universe would then be a manifestation or instantiation of these pre-existing mathematical truths. This Platonic perspective has a long philosophical tradition, dating back to the ancient Greek philosopher Plato, who argued that abstract forms or ideas were more real than the physical objects that participated in them. In the modern context, this view suggests that mathematical structures such as equations, symmetries, and geometric relationships exist independently, and that the physical universe is simply one way these structures can be realized. Some physicists have embraced versions of this mathematical Platonism. Physicist Max Tegmark has proposed that the universe simply is a mathematical structure, not something that is described by mathematics, but something that is identical to a particular mathematical object. In this view, asking where the laws of physics came from is like asking where the properties of numbers came from. They exist necessarily as features of mathematical reality. The Platonic view gains support from the apparent universality and objectivity of mathematical truths. The Pythagorean theorem is true not just in our universe, but in any conceivable universe with Euclidean geometry. The properties of prime numbers are the same regardless of whether anyone is around to discover them. Mathematical relationships seem to transcend the particular physical systems in which they are instantiated. A third possibility is that the laws of physics evolve and change over time, just like biological species or cultural institutions. In this view, the laws we observe today might be the result of a kind of natural selection operating at the level of cosmic evolution. Universes with laws that lead to instability or immediate collapse would not persist, while universes with laws that allow long-term evolution and complexity would survive and perhaps even reproduce. This evolutionary perspective on physical laws has been explored by physicists such as Lee Smolin and cosmologists working on ideas like cosmological natural selection. They propose that new universes are born from black holes in existing universes, and that the properties of the daughter universe are slightly modified versions of the properties of the parent universe. Over cosmic time, this process would lead to the evolution of physical laws that favor the formation of black holes, and therefore the production of new universes. In this scenario, the laws of physics in our universe would be the result of billions of years of cosmic evolution and selection. We observe laws that permit the formation of stars, galaxies, and black holes not because these laws are fundamental or necessary, but because only universes with such laws can successfully reproduce and pass on their properties to future generations of universes. Yet another possibility is that the laws of physics are not fixed at all, but rather represent statistical regularities that emerge from more fundamental random processes. In this view, what we interpret as rigid physical laws are actually the average behavior of countless microscopic random events. The conservation of energy, the constancy of the speed of light, and the strength of fundamental forces would all be statistical approximations that hold on large scales and over long times, but might fluctuate or vary under extreme conditions. This statistical interpretation finds some support in the foundations of thermodynamics, where the apparently rigid second law emerges from the statistical behavior of enormous numbers of particles. It also resonates with certain approaches to quantum gravity that suggest space-time itself might be an emergent phenomenon arising from more fundamental discrete processes. If physical laws are indeed statistical in nature, then they might have crystallized out of primordial chaos as the universe evolved and cooled. In the earliest moments after the Big Bang, all physical quantities might have fluctuated wildly with no fixed relationships between them. As the universe expanded and cooled, statistical patterns might have emerged and stabilized, creating the appearance of fixed physical laws. The question of where physical laws come from also connects to some of the deepest issues in the philosophy of science. What does it mean for a law to exist? Are laws descriptions of how things actually behave, or are they prescriptions that somehow compel things to behave in certain ways? Do laws govern events, or do events follow patterns that we interpret as laws? These questions become particularly acute when we consider the relationship between mathematical equations and physical reality. The equations we use to describe physical laws are human constructs, written in human languages, using human mathematical concepts. But the relationships these equations describe seem to exist independently of human awareness or understanding. How can abstract mathematical structures have the power to govern concrete physical processes? Some philosophers and physicists have suggested that this relationship works in reverse. Rather than mathematical laws governing physical processes might give rise to mathematical patterns. In this view, the universe does not follow mathematical laws. Instead, mathematics is how we describe the patterns we observe in the universe's behavior. The laws of physics would then be emergent features of reality rather than fundamental aspects of it. This emergent view of physical laws connects to ideas in complexity science and systems theory. Just as the behavior of ant colonies emerges from the interactions of individual ants, without being programmed into any single ant, the laws of physics might emerge from the interactions of fundamental components without being built into any individual component. But even if we accept that physical laws are emergent, we still face the question of why the universe has the particular emergent properties it does. Why do the interactions of quantum fields give rise to the specific conservation laws we observe? Why does the geometry of space-time follow Einstein's equations rather than some other mathematical relationship? Why do the fundamental constants have the values they do rather than different values? The multiverse concept we explored in the previous chapter offers one potential answer to these questions. If there are infinitely many universes with different physical laws, then the question of why our universe has its particular laws becomes a selection effect. We observe these laws because we exist in a universe where these laws permit the existence of observers. But even the multiverse pushes the question back one level without fully resolving it. If different universes can have different laws, what determines the range of possible laws? What constrains the multiverse itself? Is there a meta-law that governs which laws are possible and which are not? Some physicists have suggested that the deepest level of reality might be pure mathematics or pure information, with physical laws being different ways of organizing or processing this fundamental substrate. In this view, the universe would be a kind of cosmic computer, and physical laws would be the programs that this computer runs. Others have proposed that physical laws might be self-creating through a kind of cosmic bootstrap process. The laws create the universe, but the universe also creates the laws through some form of feedback or self-reference. This would make the relationship between laws and reality fundamentally circular, with neither having priority over the other. The question of where physical laws come from remains one of the deepest unsolved problems in science and philosophy. It sits at the intersection of physics, mathematics, and metaphysics, challenging our most basic assumptions about the nature of reality, existence, and explanation. While we have developed sophisticated theories about how the universe might have emerged from nothing, we have barely begun to understand how the laws that govern this emergence might themselves have come to be. Perhaps the answer lies in recognizing that the question itself might be based on false assumptions. Maybe physical laws do not come from anywhere because they do not exist as separate entities that need to be created or explained. Maybe the distinction between laws and reality between mathematical structures and physical processes is itself an artifact of how human minds organize their understanding of the world. Or perhaps the answer requires a completely new way of thinking about existence, causation, and explanation that goes beyond our current scientific and philosophical frameworks. The question of where physical laws come from might be pointing us toward a revolution in understanding as profound as those initiated by Copernicus, Darwin, or Einstein, a revolution that could transform not just our knowledge of the universe, but our understanding of knowledge itself. Our journey through the deepest mysteries of cosmic origins has led us to a startling possibility. What if the very question that launched our investigation, how something can come from nothing, is based on a fundamental misunderstanding? What if nothing, in the absolute sense we have been considering, is not just unlikely or unstable, but actually impossible? This radical idea turns our entire inquiry on its head and suggests that existence might be the natural state of affairs, while true nothingness would be the anomaly requiring explanation. The possibility that nothing is impossible emerges from several different lines of thought that we have encountered throughout our exploration. From quantum mechanics, we learned that even empty space is filled with fluctuating fields and virtual particles. From philosophy, we discovered the logical difficulties in coherently conceiving of absolute nothingness. From cosmology, we found that the universe might have zero total energy, making its existence energetically costless. Each of these insights chips away at our intuitive notion that nothing is simple and something is complex. Let us begin by examining the logical arguments against the possibility of absolute nothingness. These arguments have a long history in philosophy, dating back to ancient thinkers who wrestled with the relationship between being and non-being. The basic logical problem is that absolute nothingness seems to be self-refuting. To define absolute nothingness, we must give it properties, but having properties contradicts its nature as having no properties. Consider what absolute nothingness would have to be. It would have no space, no time, no matter, no energy, no fields, no laws, no mathematics, no information, no potential, no possibilities, no structure, no relationships, and no existence of any kind. But the moment we say that absolute nothingness has no space, we have attributed to it the property of lacking space. When we say it has no time, we give it the property of timelessness. Each description of what absolute nothingness lacks becomes a positive description of what it is like. This leads to what philosophers call the problem of negative properties. Can something truly have the property of lacking all properties? Is the absence of existence itself a form of existence? The very fact that we can think about absolute nothingness, discuss it, and reason about it seems to give it a kind of conceptual reality that contradicts its supposed nature as complete absence. Some philosophers have argued that this problem is merely linguistic or conceptual rather than metaphysical. They suggest that our difficulty in describing absolute nothingness reflects the limitations of human language and thought rather than any deep truth about the impossibility of nothingness itself. After all, we can think about many things that do not exist, from unicorns to perpetual motion machines, without thereby bringing them into being. But other philosophers have argued that the problem runs deeper than language. They suggest that absolute nothingness is not just difficult to describe, but is genuinely incoherent as a concept. In this view, the idea of absolute nothingness violates basic principles of logic and meaning. It is not just that we cannot adequately describe nothingness, but that there is nothing coherent to describe. The physicist and philosopher David Albert has offered a particularly influential argument along these lines. He points out that in physics, what we call empty space or vacuum is never truly empty, but always contains quantum fields with their associated energy and structure. Even if we could somehow remove these fields, we would still be left with the geometric structure of space-time itself. And even if we could eliminate space-time, we would still have the mathematical and logical frameworks within which the concept of elimination has meaning. Albert argues that every attempt to conceive of absolute nothingness leaves behind some residual structure or framework. We cannot eliminate everything without eliminating the very concepts and logical principles that make elimination possible. This creates what he calls an infinite regress of elimination, where each step toward absolute nothingness reveals new layers of structure that must themselves be eliminated. From the perspective of quantum mechanics, the impossibility of nothing takes on a different character. The uncertainty principle tells us that certain pairs of quantities cannot be simultaneously determined with perfect precision. This applies not just to the position and momentum of particles, but to the very existence and non-existence of fields and particles themselves. In quantum field theory, the vacuum state is not a state of absolute emptiness, but rather the state of minimum energy consistent with the uncertainty principle. Even in this minimum energy state, quantum fields are fluctuating, creating and destroying virtual particles in accordance with the fundamental randomness of quantum mechanics. These fluctuations are not optional features that could be turned off. They are mandatory consequences of the mathematical structure of quantum theory. Some physicists have argued that this quantum mechanical impossibility of absolute emptiness extends to the question of cosmic origins. If quantum fields must always be fluctuating, and if these fluctuations can sometimes grow large enough to create universes, then the absence of everything would be inherently unstable. Absolute nothingness would immediately decay into something through quantum processes. This idea connects to the concept of symmetry breaking in physics. Many physical systems naturally evolve from symmetric states to asymmetric states because the symmetric state is unstable. A pencil balanced on its point will fall in some direction because the balanced state, while perfectly symmetric, cannot maintain itself against the slightest disturbance. Similarly, absolute nothingness might be perfectly symmetric but inherently unstable. Any tiny fluctuation, any infinitesimal deviation from perfect nothingness would grow and amplify until something definite emerged. In this view, the existence of something rather than nothing would be inevitable because nothingness cannot maintain itself against its own internal instabilities. The mathematician and philosopher Charles Sanders Peirce proposed a version of this argument in the 19th century. Peirce suggested that absolute nothingness would have no laws or constraints to prevent something from arising. In the complete absence of any prohibition against existence, existence would be not just possible, but inevitable. Nothing would be unstable precisely because it would lack the structure necessary to maintain itself as nothing. This perspective receives some support from our understanding of phase transitions in physics. When water freezes into ice, or when a magnetic material becomes magnetized, the system transitions from a symmetric state to a less symmetric state through a process called spontaneous symmetry breaking. The initial symmetric state is often unstable, and the system naturally evolves toward a more stable asymmetric configuration. If we think of absolute nothingness as a kind of ultimate symmetric state, then the emergence of something might be analogous to a cosmic phase transition. The nothingness state would be inherently unstable, and any tiny perturbation would cause it to break down into definite structures and patterns. The universe would not need to be created from nothing. It would emerge naturally from the instability of nothingness itself. But the argument for the impossibility of nothing faces significant challenges. Critics point out that logical arguments alone cannot determine what is physically possible. Just because we have difficulty conceiving of absolute nothingness does not mean it cannot exist. Mathematics is full of concepts that are difficult or impossible to visualize, but are nonetheless well-defined and useful. Moreover, the quantum mechanical arguments assume that quantum mechanics itself is fundamental and universal, but quantum mechanics might be an emergent theory that applies only within certain domains or under certain conditions. At the deepest level of reality, different principles might apply that do not prohibit absolute nothingness. The impossibility arguments also seem to prove too much. If absolute nothingness is impossible, then why is there this particular something rather than some other something? Why does the universe have the specific properties and laws we observe rather than different properties and laws? The impossibility of nothing might explain why something exists, but it does not seem to explain why this particular something exists. Some philosophers have responded to this challenge by arguing that all possible somethings do exist, corresponding to the mathematical multiverse we encountered in previous chapters. In this view, every mathematically consistent structure exists as a physical reality, and our particular universe is just one member of this infinite ensemble. The impossibility of nothing would then explain not just why something exists, but why everything that can exist does exist. The question of whether nothing is possible also connects to deep issues in mathematics and logic. The concept of the empty set, the set that contains no elements, is fundamental to modern mathematics. But even the empty set has properties and relationships with other mathematical objects. It is not absolute nothingness, but rather a particular kind of something, a structured absence that plays a definite role in mathematical systems. Some mathematicians and philosophers have argued that this points to a fundamental principle. Even the most minimal mathematical structures, even the representation of absence or emptiness, require some framework of rules and relationships. Mathematics cannot begin from absolute nothingness, because mathematical thinking requires logical principles, symbolic systems, and conceptual frameworks that are themselves forms of structure and existence. This leads to what some call the principle of plenitude. If mathematical structures necessarily exist in some sense, and if physical reality corresponds to mathematical structures, then all possible realities must exist. The impossibility of absolute nothingness would imply the necessity of everything that can possibly exist. The principle of plenitude connects to ancient philosophical arguments about the relationship between possibility and actuality. The philosopher Leibniz argued that this is the best of all possible worlds, because an infinitely good God would necessarily actualize the best possibility. Modern versions of this argument suggest that all possibilities are actualized not because of divine choice, but because the complete absence of actualization, absolute nothingness, is impossible. Yet the principle of plenitude raises its own puzzles. If everything possible exists, what determines what is possible? Are there constraints on possibility itself, and where do these constraints come from? The impossibility of nothing might eliminate one mystery, only to replace it with another, equally profound mystery about the nature of possibility and necessity. The debate over whether nothing is possible also intersects with questions about the nature of existence itself. What does it mean for something to exist? Does existence come in degrees, or is it an all or nothing property? Can something exist in some senses but not in others? These questions become particularly acute when we consider abstract objects like numbers, logical principles, and mathematical structures. Do these exist in the same way that particles and fields exist? If they exist in some different sense, what is the relationship between mathematical existence and physical existence? And if they exist in the same sense, then absolute nothingness would have to eliminate not just physical reality, but abstract reality as well. The possibility that nothing is impossible suggests a radical reframing of the entire question of cosmic origins. Instead of asking how something came from nothing, we might ask how this particular something emerged from the space of all possible somethings. Instead of seeking the cause that brought the universe into existence, we might investigate the principles that selected this universe from among all possible universes. This reframing does not make the mystery of existence disappear, but it does transform it. The mystery becomes not the mystery of why anything exists, but the mystery of why existence takes the particular forms it does. The impossibility of nothing would make existence inevitable, but it would not make any particular form of existence inevitable. As we approach the conclusion of our investigation, we find ourselves in a strange position. We began by asking how something could come from nothing, but we have discovered that the question itself might be based on a false premise. Nothing, in the absolute sense we initially imagined, might be not just absent, but impossible. Existence might be the default state of reality, while absolute nothingness would be the anomaly that requires explanation. We have traveled to the very edge of human knowledge, exploring quantum fluctuations and cosmic inflation, investigating scientific models of universe creation, contemplating infinite multiverses, and questioning the very possibility of absolute nothingness. Now, as we reach the end of our journey, it is time to confront the ultimate question that has guided our exploration. How did the universe begin from nothing? What can we say with confidence about the deepest mystery of existence itself? The honest answer, humbling as it may be, is that we do not yet know. Despite centuries of scientific progress and decades of sophisticated theoretical work, the ultimate origin of our universe remains shrouded in mystery. We have developed remarkable theories that can trace cosmic history back to the first tiny fraction of a second after the Big Bang. But the very beginning, the moment of creation itself, lies beyond our current understanding. Yet our journey has not been in vain. While we cannot definitively answer how the universe began from nothing, we have learned something equally profound. We have discovered that the question itself is far more complex and subtle than it first appeared. The concepts of something and nothing, of beginning and causation, of existence and non-existence, turn out to be much more mysterious than our everyday experience would suggest. Let us review what we have learned about the nature of nothing. Our investigation revealed that nothing is not the simple absence we might naively imagine. Even empty space, the closest thing to nothing that we can observe, is filled with quantum fields, virtual particles, and zero-point energy. The vacuum is not passive or inert, but active and creative, constantly generating and destroying particle pairs in accordance with the uncertainty principle. More profoundly, we discovered that absolute nothingness, the complete absence of everything including space, time, matter, energy, fields, and laws, may not even be a coherent concept. Logical arguments suggest that absolute nothingness might be self-refuting, requiring properties and structures that contradict its nature as the absence of all properties and structures. Quantum mechanics suggests that perfect emptiness is prohibited by the fundamental randomness that governs all physical processes. If absolute nothingness is indeed impossible, then the question of how something came from nothing is transformed. Instead of asking how existence emerged from non-existence, we might ask how this particular form of existence emerged from the space of all possible forms of existence. The mystery shifts from the mystery of existence itself to the mystery of why existence takes the specific form we observe. Our exploration of quantum mechanics revealed that the boundary between something and nothing is not sharp or absolute, but fuzzy and dynamic. Virtual particles pop in and out of existence on timescales so brief that they seem to violate the conservation of energy, yet they have measurable effects on the physical world. The quantum vacuum is neither something nor nothing in any classical sense, but rather a strange hybrid that partakes of both. This quantum fuzziness extends to the question of cosmic origins. If the universe has zero total energy, with the positive energy of matter and radiation exactly balanced by the negative energy of gravitational attraction, then its creation would not violate conservation laws. The entire universe could be a quantum fluctuation that borrowed zero net energy from the vacuum and therefore never needs to pay it back. But even a zero-energy universe raises questions about the mechanism of its creation. How could a fluctuation large enough to contain our entire observable cosmos arise from the quantum vacuum? The answer, we discovered, lies in cosmic inflation, the period of exponential expansion that could have stretched a tiny quantum fluctuation to cosmic proportions in an incredibly brief time. Inflation solves not just the problem of cosmic size, but also the problems of cosmic structure, uniformity, and geometry. It explains why the universe appears flat, why it has the same temperature in all directions, and why it contains the density fluctuations that later grew into galaxies and stars. Most remarkably, inflation connects the quantum world of subatomic particles to the cosmic world of galaxies and superclusters, showing how microscopic randomness can generate macroscopic structure. The combination of quantum mechanics and inflation leads naturally to the concept of eternal inflation and the multiverse. If quantum fluctuations can create inflating regions of space, and if these regions can spawn new inflating regions through additional fluctuations, then the process might continue indefinitely. Our universe would be just one bubble in an infinite foam of universes, each with its own properties and history. This multiverse perspective offers a potential solution to the puzzle of cosmic fine-tuning. The physical constants and laws of nature appear to be precisely adjusted to allow the existence of stars, planets, atoms, molecules, and life itself. In a single universe, this fine-tuning might seem to require explanation or design. But in a multiverse with infinite variety, some universes will inevitably have the right properties for complexity and life. We observe a life-friendly universe not because it was designed for us, but because only life-friendly universes can be observed by living beings. Yet the multiverse pushes the mystery back, rather than eliminating it. If different universes can have different laws of physics, what determines which laws are possible? What constrains the multiverse itself? We found ourselves confronting the deepest question of all. Where do the laws of physics come from? This question led us into the realm where physics meets philosophy and mathematics. Are the laws of physics discovered or invented? Do they exist independently of the physical universe? Or do they emerge from more basic features of existence? Are they necessary consequences of the fact that something exists rather than nothing? Or are they contingent features that could have been different? We explored several possibilities. The laws might be emergent properties that arise naturally from the basic fact of existence, like the rules of logic that seem necessary for any coherent system of thought. They might be fundamental mathematical structures that exist in some abstract realm and find expression in physical reality. They might evolve and change over cosmic time through a kind of natural selection operating at the level of universes. Or they might be statistical regularities that emerge from more fundamental random processes. Each of these possibilities offers insights, but none provides a complete answer. The question of where physical laws come from may be unanswerable within the framework of current science, requiring new conceptual frameworks that we have not yet developed or perhaps cannot develop, given the limitations of human cognition. Our investigation also revealed the provisional and speculative nature of many ideas about cosmic origins. The scientific models we explored, from quantum tunneling to the Hartle-Hawking no-boundary proposal to brain-world scenarios, are highly theoretical and largely untestable with current technology. They represent the best efforts of brilliant scientists to push beyond the limits of established knowledge, but they remain more like informed speculations than established scientific facts. This does not diminish their value or importance. Science progresses by proposing bold hypotheses that extend beyond confirmed knowledge, testing these hypotheses against observation and experiment, and gradually building a more complete understanding of the natural world. The speculative theories of today may become the confirmed science of tomorrow, just as the speculative ideas of Einstein and other pioneers became the established foundations of modern physics. But it does counsel humility about what we can claim to know about cosmic origins. We are still in the early stages of understanding how the universe began, and it is possible that the ultimate answer will require conceptual revolutions as profound as those initiated by Copernicus, Darwin, or Einstein. The question of how something came from nothing may be pointing us toward discoveries that will transform not just our knowledge of the cosmos, but our understanding of existence itself. What we can say with confidence is that the universe we observe today has been expanding and cooling for nearly 14 billion years. We can trace this cosmic evolution back to a time when the entire observable universe was compressed into a region smaller than an atom, with temperatures and densities so extreme that normal matter could not exist. We can map the cosmic microwave background radiation and see the imprints of quantum fluctuations that occurred in the earliest moments of cosmic history. We can also say that the universe appears to be governed by elegant mathematical laws that connect the behavior of the smallest particles to the evolution of the largest structures. These laws show a remarkable unity and consistency, suggesting that reality has a deep underlying order that we are gradually learning to understand and appreciate. But beyond these observational facts and tested theories, we enter the realm of informed speculation. The ultimate beginning, the moment of creation itself, remains hidden behind a veil of ignorance that may prove impenetrable to scientific investigation. The questions we can ask may exceed the questions we can answer, and the mysteries we uncover may be deeper than the mysteries we solve. Yet this is not cause for despair, but for wonder. The fact that the universe is mysterious does not diminish its majesty, but enhances it. The fact that existence itself is puzzling does not make it less real, but more astonishing. We find ourselves in a cosmos that is stranger, more creative, and more amazing than our ancestors could have imagined, and our growing knowledge reveals new depths of mystery, rather than eliminating mystery altogether. Perhaps the most profound lesson of our journey is that the universe is not required to make sense to us. It is not obligated to conform to our intuitions, satisfy our expectations, or answer our questions in ways we can easily understand. The cosmos operates according to its own principles and patterns, and our task as curious beings is to adapt our thinking to the reality we find, rather than expecting reality to adapt to our preconceptions. The question of how the universe began from nothing has led us to the frontiers of human knowledge and beyond. It has shown us that nothing is not simple, that something is not inevitable, and that existence itself is the deepest mystery we can contemplate. Whether the universe emerged from quantum fluctuations, tunneled from absolute nothingness, arose from mathematical necessity, or came into being through processes we have not yet imagined, its mere existence remains the most astonishing fact we know. In the end, the universe does not owe us an explanation for its existence. The fact that we are here to ask the question, to wonder about our origins, to contemplate the mystery of being itself, is perhaps more remarkable than any answer we might discover. We are the universe becoming conscious of itself, matter and energy organized in such a way that they can reflect on their own existence and ponder the deepest questions of reality. The journey from nothing to something, from simplicity to complexity, from unconsciousness to awareness, represents the most extraordinary transformation we can conceive. Whether this transformation was inevitable or accidental, necessary or contingent, designed or emergent, it has produced beings capable of asking how it all began. In that capacity for wonder and questioning, we find both the deepest mystery and the greatest gift of existence itself. We began our journey with a simple question that has haunted humanity since we first gazed up at the stars and wondered about our place in the cosmos. Why is there something rather than nothing? How did everything we see around us, from the smallest atoms to the largest galaxies, emerge from what appears to be complete absence? This question seems straightforward enough, rooted in our everyday experience of things appearing and disappearing, being created and destroyed. But as we have discovered together, the question is anything but simple. Our exploration has taken us through the strange world of quantum mechanics, where empty space seethes with activity and virtual particles dance in and out of existence. We have journeyed to the earliest moments of cosmic history, where space itself expanded faster than light, and tiny quantum fluctuations grew to become the seeds of galaxies. We have contemplated infinite multiverses where every possibility is realized, and we have questioned whether absolute nothingness is even a coherent concept. What we have found is that nothing is not nothing. The absence we thought we understood turns out to be filled with potential, structure, and creative power. Even the emptiest regions of space are pregnant with possibility, ready to give birth to particles, fields, and perhaps entire universes. The vacuum is not a passive backdrop against which the drama of existence unfolds, but an active participant in the cosmic story, constantly creating and destroying, fluctuating and evolving. This discovery transforms our understanding of cosmic origins. We no longer need to explain how something magical happened to bring the universe into existence from pure nothingness. Instead, we can begin to understand how the creative potential inherent in the quantum vacuum, amplified by cosmic inflation and guided by the deep mathematical structures that govern reality, gave rise to the rich and complex universe we observe today. The universe, it turns out, may not have been created from nothing, but rather from a nothing that was never truly empty. The quantum fields that fill even the most perfect vacuum carry within them the seeds of galaxies, stars, planets, and life itself. What we call the beginning of the universe may have been not a moment of creation from absolute void, but a moment when the hidden creativity of apparently empty space suddenly blossomed into the magnificent cosmos we inhabit. This realization does not make the universe less mysterious or miraculous. If anything, it makes existence even more astonishing. The fact that the deepest emptiness is filled with creative potential, that the most fundamental laws of physics seem precisely tuned to allow complexity and consciousness to emerge, that we find ourselves in a universe capable of contemplating its own origins, these remain among the most profound mysteries we can contemplate. Our journey has also revealed the remarkable power of human curiosity and intelligence. Through mathematics and physics, through careful observation and bold theoretical leaps, we have been able to peer back to the very edge of time itself. We have traced the history of the universe from its current state of expansion and cooling back to moments when it was smaller than an atom and hotter than the core of any star. We have developed theories that connect the quantum world of subatomic particles to the cosmic world of galaxies and dark energy. Yet our investigation has also shown us the limits of current knowledge and the vast territories that remain unexplored. We do not know what caused cosmic inflation or what the inflaton field actually is. We cannot definitively say whether the multiverse exists or whether our universe is unique. We do not understand where the laws of physics come from or why they have the particular mathematical forms we observe. The deepest questions about existence, causation, and the nature of reality itself remain open. This is as it should be. Science progresses not by providing final answers, but by asking better questions, by revealing new mysteries hidden within familiar phenomena, by showing us that reality is stranger and more wonderful than we had imagined. Each discovery opens new frontiers of ignorance. Each answer reveals new questions we had not known how to ask. The question of how the universe began from nothing has led us to some of the most profound insights in modern science. We have learned that space and time are not fixed stages on which physical processes occur, but dynamic entities that can expand, contract, and curve. we have discovered that matter and energy are different manifestations of the same underlying reality, and that this reality emerges from quantum fields that permeate all of existence. We have found that the universe is not just stranger than we imagine, but stranger than we can imagine, operating according to principles that challenge our deepest intuitions about causation, locality, and the nature of existence itself. Particles can tunnel through barriers they should not be able to cross. Empty space can give birth to real particles. The act of observation can influence the properties of distant objects. Reality refuses to conform to the neat categories of common sense. But perhaps the most important lesson of our journey is that we are part of the story we are trying to understand. We are not external observers looking in at the universe from some privileged position outside of space and time. We are the universe looking at itself, matter and energy, organized in such a way that they can contemplate their own existence and wonder about their origins. This changes everything about how we think about cosmic origins. We are not asking how some external agent created the universe from nothing. We are asking how the universe created itself, how it organized itself into patterns of such complexity that parts of it became conscious and began to question the nature of existence itself. We are the universe's way of knowing itself, its method for exploring the deepest questions about reality. In this light, our quest to understand how something came from nothing is not just an intellectual exercise, but an expression of the cosmos's own drive towards self-understanding. Every equation we write, every experiment we perform, every moment of wonder we experience as we contemplate the night sky, these are all ways that the universe explores its own nature and celebrates its own existence. The beauty of this perspective is that it makes every conscious being a participant in the grandest story ever told. We are not accidents or afterthoughts in a universe that would be essentially the same without us. We are the universe becoming aware of itself, the cosmos developing the capacity for wonder, knowledge, and appreciation of its own magnificent complexity. Whether the universe emerged from quantum fluctuations in an eternally inflating multiverse, tunneled into existence from absolute nothingness, arose from the collision of higher dimensional brains, or came into being through processes we have not yet discovered, the fact remains that it has produced beings capable of asking these questions. In our curiosity about cosmic origins, we see the universe's own curiosity about itself. This does not mean that consciousness or intelligence were inevitable outcomes of cosmic evolution. The path from quantum fields to thinking beings required countless contingent events, precise balances of forces, and perhaps extraordinary luck. But it does mean that our existence connects us intimately to the deepest processes that govern reality. We carry within our minds and bodies the history of the cosmos itself, from the first moments after the Big Bang to the present day. The atoms in our bodies were forged in the cores of ancient stars and scattered across space when those stars exploded as supernovas. The carbon that forms the backbone of our DNA, the calcium in our bones, the iron in our blood, all were created by nuclear processes in stellar furnaces billions of years ago. We are literally made of star stuff, as astronomer Carl Sagan so memorably put it. But we are more than just collections of stellar debris. We are patterns of organization so complex that they can model the universe itself, can understand the laws that govern cosmic evolution, can appreciate the beauty of mathematical relationships that describe reality at its deepest levels. We are the way the universe has learned to think about itself. As we conclude our exploration of how the universe began from nothing, we find ourselves not with a final answer, but with a transformed understanding of the question itself. Nothing, we have learned, is not the simple absence we thought it was. Something is not the arbitrary accident it might have seemed. The boundary between existence and non-existence is not sharp but fuzzy, not fixed but dynamic, not absolute but relative. The universe we inhabit is far stranger, more creative, and more wonderful than the mechanistic clockwork cosmos imagined by earlier generations of scientists. It is a universe where empty space is full of potential, where the impossible becomes merely improbable, where consciousness emerges from complexity and looks back with wonder at the process that created it. We ask how something came from nothing, but what we find is that nothing was never truly empty. It had structure, potential, law, and perhaps even necessity. The beginning of the universe may not have been an accident that requires explanation, but a feature of the deepest truths we have yet to understand. In our questions about cosmic origins, we hear the echo of the universe questioning itself. In our wonder at the fact of existence, we participate in existence celebrating its own reality. In our search for understanding, we embody the cosmos's drive toward greater complexity, consciousness, and self-awareness. The mystery of how something came from nothing remains unsolved, but it has revealed itself to be a far richer and more profound mystery than we initially imagined. It is a mystery that connects quantum mechanics to cosmology, mathematics to physics, consciousness to cosmos. It is a mystery that makes us not just observers of the universe, but participants in its ongoing story of self-discovery. And perhaps that is the most beautiful truth we have uncovered in our journey. We are not separate from the mystery we seek to understand. We are part of it, expressions of it, manifestations of the universe's own endless creativity and boundless capacity for wonder. In asking how something came from nothing, we participate in the universe's eternal conversation with itself about the nature of existence, reality, and the magnificent mystery of being.